Hello everyone. Today I Jyoti of class MSc Chemistry first year is here to read out a chapter from physical chemistry, and this chapter is from unit 4, and the name of the chapter is ion transport and solutions. First topic is ionic movement under the influence of an applied electric force. First is treatment of ions without electric field. The ions in solution shows zigzag or random movement in all possible directions equally. Collision are also present, but the mean displacement of ions is zero, that is, there is no net drift of the ions. Second, treatment of ions in electric field. Ions show preferential ionic movements, that is, in one direction in space which is parallel to the field. Ionic movement is not random. The positively charged particles prefer to move towards negatively charged electrode, and negatively charged particle move towards positively charged electrode. The ions will drift, that is, movement of ions in electric field is affected by the fact that they are charged. Next is diffusion. It is a random motion according to Newton's second law of motion. If there is no force, there is no motion. This random motion will also be due to any force. This force may be chemical potential or free energy or work done. W is equals to F into dx, or we can say that W by dx is equals to force, or we can say that force is equals to du, where U is chemical potential, F is force, W is work done, and x is displacement. Next is average value of the drift velocity. After collision, any ion starts moving randomly with the velocity, and that may be in any direction, not in the preferred motion. Therefore, the initial velocity does not contribute to the drift of the ion, but the ions are under the influence of applied electric field. This provides an extra velocity component in the same direction of the applied force F vector. This additional velocity component due to the force F vector is called drift velocity Vd. According to Newton's second law, electric force field will accelerate the ions. F is equals to ma, equation 1, and acceleration is the rate of change of velocity, that is, a is equals to dB by dt. Also, F vector by m is equals to a. Therefore, F vector by m is equals to dB by dt. This is equation 2. If n is the number of collisions occur in a time t, then time between collisions is random. It can be small, it can be long time interval. Average time between collisions is tau is equals to t by n. The average value of drift velocity Vd is equals to acceleration into average time between collisions. Vd is equals to acceleration into tau. This is equation 3. Vd is equals to dv by dt into tau. Therefore, Vd is equals to F vector by m into tau. This is equation 4. According to this relation, Vd is directly proportional to force vector, hence drift velocity is directly proportional to driving force of electric field. The flux of the ions is related to the drift velocity as flux is equals to concentration of ions into drift velocity. Flux, it is the amount of ions passing through unit plane per second. Vd is directly proportional to F, therefore flux is directly proportional to electric force. Next topic is mobility of ions. First is drift velocity. When randomly moving ions are subjected under an applied force F, they acquire directed component of velocity, that is Vd is equals to drift velocity. Vd is directly proportional to F vector. From equation 4, we can write Vd is equals to F vector by m into tau. That is Vd by F vector is equals to tau by m, which is equation 5th. So tau by m is the proportionality constant called absolute mobility, which is represented by U absolute. Therefore, U absolute, measure of the drift velocity acquired by ions under the influence of force F vector. U absolute is equals to tau by m, which is equals to Vd by F vector, which is equation 6. That is, U absolute is drift velocity developed per unit applied force. F vector is equals to 1 dyne. Unit of U absolute is equals to centimeter or second or dyne. The electric force F operating an ion is equals to charge on X electric field. F vector is equals to Zi E naught X, equation number 7. F vector is equals to Zi E naught X by 300 dynes, which is equation number 8. Or we can say that U absolute is equals to Vd by F, which is equals to Vd by Zi E naught x, where Vd by x is equals to U conventional. U absolute is equals to U conventional by Zi E naught, which is equation number 9. Therefore, U conventional is equals to U absolute into Zi E naught, equation number 10. U conventional is equals to U absolute into Zi E naught by 300. The concept of absolute mobility is more general because it can be used for any force that determines the drift velocity of ions, and not only the electric force used in the definition of conventional mobility. That is, conventional mobility is defined as the drift velocity in unit electric field. Next topic is directed ionic movement and current, or we can say ionic drift velocity and its relation with current density. The concept of Vd, drift velocity, can be used to obtain expression for ionic current density flowing through an electrolyte in external applied magnetic field expression. Consider a reference plane of unit area. Both the positive and negative ions will drift across this plane. Firstly, consider the positive ions and let their drift velocity be plus. So flux of positive ions is equals to concentration of positive ions into Vd plus. Tau plus is equals to C plus V plus. Equation number 1. The current density of positive ions, the flow of charge across the plane due to the flux of the positive ions. J plus is equals to J plus Z plus F, where capital J plus is equals to flux, Z is equals to charge on 1 mole of ion, F is equals to Faraday constant. Small j plus is equals to C plus V plus Z plus F, which is equation number 2. This is the contribution of positive ions. Only other ions sphere will make their own contributions of current density. The current density due to the ith species will be J vector ith is equals to Ci Vi Zi F, which is equation number 3. And the total current density due to the contribution of all the ionic species is J vector is equals to summation I Ji vector, which is equals to summation I Zi F Ci Vi. Equation number 4. For A Z ratio Z valent electrolyte, Z plus is equals to Z minus, which is equals to Z. C plus is equals to C minus, which is equals to C. Therefore, small j vector is equals to Z into Fc, bracket V plus V minus, equation number 5. Next topic, we have specific and equivalent conductivities in terms of ionic mobilities. Substituting the value of drift velocity Vt is equals to V concentration into X in the equation. J is equals to summation I Zi F Ci Vi for current density. J is equals to summation Zi Fi Ci U conventional I into X, which is equation number 3. We know specific conductivity is equals to sigma is equals to I by X, which is equals to summation Zi Fci bracket U conventional I, equation number 7. For A Z ratio Z valent electrolyte, uh, conductivity is equals to ZFC bracket U conventional plus minus U conventional plus, which is equation number 8. Conclusions. The specific conductivity of an electrolyte cannot be an concentration independent constant as it is in case of metals. It will be vary because the number of moles of ion per unit volume C can vary with in an electrolyte solution. Second is specific conductivity can be related to the molar and equivalent conductivities. For A Z ratio Z valent electrolyte, it is found that molar conductivity is equals to conductance by concentration, which is equals to ZF bracket U conventional plus U conventional minus, equation number 9, and equivalent conductivity is equals to molar conductivity by Z, which is equals to F bracket start U conventional plus U conventional minus, which is equation number 10. This equation shows that the equivalent conductivity will be in constant independent of concentration if the mobility does not vary with concentration. However, the ion-ion interactions prevent the electrical mobility being a constant. Hence, the equivalent conductivity must be in function of concentration. Next topic is the Einstein relation between the absolute mobility and the diffusion coefficient. The process of diffusion results from the random walk of ions. The process of the migration results from the drift velocity acquired by ions when they experience a force. The drift of ions does not avoid their random walk, in fact, it is superimposed on their random walk. Next topic is Einstein realized that the drift velocity and the random walk are linked and deduced an important relation between absolute mobility U absolute, which is a quantitative characteristic of the drift, and the diffusion coefficient D, which is a quantitative characteristic of the random walk. Both diffusion and conduction are non-equilibrium process and therefore not responsible to the methods of equilibrium thermodynamics where the concepts of time and charge are absent. However, it is possible to that the two processes oppose and balance each other and a pseudo equilibrium is obtained. Consider a solution of an electrolyte Mx to which a certain amount of radioactive M positive ions are added in the form of the salt Mx. Consider a concentration gradient of the tagged species so that its diffusion flux Jd is given by the Fick's first law. Jd is equals to minus d capital D dc by dx, equation number 1. Now let an electric field be applied and each tagged ion feels the field and the drift velocity is Vd is equals to U absolute into F vector. This produces a current density given by small j vector is equals to Z plus Vd into Fc, equation number 3. That is a conduction flux Jc that is obtained by dividing the conduction current density J small j vector by the charge per moles of ion. Jc is equals to small g vector by Zf, which is equals to C into drift velocity. But Vd is equals to U absolute, which is equals to Jc is equals to C U absolute into F vector. The applied field is adjusted so that the conduction flux exactly compensates for the diffusion flux. Jd is equals to minus Jc, which is equation 5, minus capital D dc by dx plus C U absolute into F vector is equals to 0. That is dc by dx is equals to C into U absolute into F vector by capital D, which is equation number 6. This situation may be regarded as similar to equation because there is no net flux or transport of ions. Hence the Boltzmann law can be used. Since the potential varies along the x direction, the concentration of ions at any distance x is C is equals to C naught E epsilon power minus U by kT, equation number 7. U is potential energy of an ion is applied field. U C naught is concentration where the potential energy is 0. Differentiating both sides with respect to x, we get dc by dx is equals to minus C naught epsilon power minus v by x into 1 by kt into du by dx, which is equals to minus c by kt into du by dx, which is equation number 8. But we know f vector is equals to minus du by dx. Hence dc by dx is equals to plus c by kt into f vector. Comparing this equation with dc by dx is equals to c into u absolute into f vector by capital D, we get u absolute by capital D is equals to 1 by kt, or we can say that D is equals to u absolute into kt. This is an Einstein equation. Importance: phenomenological treatment of diffusion coefficient BRT is equals to capital D, equation 11, where B is undetermined phenomenological coefficient. Combining the above equations, we get BRT is equals to U absolute into KT, equation 12. B is equals to U absolute KT by RT, which is equals to U absolute by NA. Therefore, NA into K is equals to R. It explains various other phenomena, forces that produces drift velocities. Two such forces are the force experienced by an ion when it overcomes the viscous drag of a solution and the force arising from an applied electric field. Thus, the diffusion coefficient linked to the viscosity, the Stokes Einstein relation, and to the equivalent conductivity, the Nernst Einstein relation. Next topic is drag or viscous force acting on an ion in solution. Einstein asserted the similarity between a macroscopic sphere moving in an incompressible fluid and a particle, example an ion, moving in a solution. The macroscopic sphere experiences a viscous or drag force that opposes its motion. Value of the drag force depend on velocity v, d diameter, viscosity n, and density of medium. Reynolds number Re is equals to Vd into P by N. This is equation number 1. Here, when the hydrodynamic conditions are such that Re is very less than 1, Stokes showed that the drag force F opposing the sphere is given by F is equals to 6 pi n into R into V, which is Stokes law, when d ion is equals to diameter of ion is 10 to the power minus 8 centimeter, V of ion is Vd, which is equals to 10 to the power 4 centimeter second inverse, and n is equals to 10 to the power minus 2, and uh, rho is 1, then Re is equals to 10 to the power minus 10. Thus, the hydrodynamic condition Re very less than 1 requires for the validity of Stokes' law is easily satisfied by an ion in solution. If the moving particles is cylindrical and not spherical, the factor 6 pi should be replaced by 4 pi. Next topic is application of Stokes-Einstein relation. First, it is used in classical work of Perrin. He watched random work of a colloidal particles and from mean square distance traveled in a time 2t, he obtained the diffusion coefficient as d is equals to x square by 2t. Secondly, determination of Avogadro's number from Stokes-Einstein-Boltzmann constant can be obtained as k is equals to 6 pi n r capital D by capital T, but k is equals to r by na, Avogadro number, where Avogadro number is equals to r by k. Thus na, Avogadro number, is equals to rt by 6 pi n r into capital D. Hence Avogadro number can be determined. Third is derivation of U conventional. We know that U observed is equals to 1 by 6 pi n r, and U conventional is equals to U observed into Z I E naught. Thus, U conventional is equals to Z I E naught by 6 pi n r, also known as Stokes mobility. Next topic is limitation of Stokes-Einstein relation. Firstly, it does not consider movement of ions under electric field. Rather, the Stokes law is derived from a macroscopic sphere moving in an incompressible liquid. Secondly, the existence of a charge on a moving body has the following effect on polar solvent. It tends to produce an orientation of solvent dipoles in the vicinity of the ion. Since the charge is moving, once oriented, the dipole takes some finite relaxation time tau to disorient. Secondly, during this relaxation time tau, a relaxation force operates on the ion which is equivalent to an additional frictional force on the ion and results in expression for the drag force of the from F is equals to 6 pi n RV minus 6 pi n S by E, where S is equals to 4 by 9 into tau by 6 pi n into E naught square by R cube, and E is dielectric constant of the medium. Then the force 6 pi n V into S by E contribute only 25% and is neglected while deriving the Stokes-Einstein relation. Next topic is Stokes-Einstein relation. Consider a macroscopic sphere is moving in an incompressible fluid medium whose viscosity is n. It will experience a viscous or drag force that opposes its motion, and Stokes shows that the drag force F opposing the sphere is given by Stokes' law as F vector is equals to 6 pi n r vd, where v is velocity of macroscopic sphere, r is radius of sphere, and n is viscosity of medium. When diffusion is occurring, it can be considered that there is a driving force where F vector is equal to minus du by dx operating on the particles. The driving force produces a steady state diffusion flux J. In this steady state condition, the diffusional driving force must be opposed by an equal resistance force, that is Stokes viscous force. From equation 1 and 2, we can say that minus du by dx is equal to 6 pi n r into v into d. So the absolute mobility u absolute for the diffusing particles is given by dividing the drift velocity by either the diffusional driving force or Stokes viscous force. U absolute is equal to drift velocity by diffusional driving force, which is equation 4. U absolute is equal to Vd by minus du by dx, which is equals to Vd by 6 pi n r Vd, which is equals to 1 by 6 pi n r. Thus, U absolute is equals to 1 by 6 pi nr, which is equation number 5. We know the expression relating the diffusion coefficients and the absolute mobility is U absolute is equals to d by kt, or we can say that d is equals to U absolute into kt, which is equation number 6. From 5 and 6, the Stokes-Einstein relation is capital D is equals to kt by 6 pi n into r, equation 7. It links the process of diffusion and viscous flow. Next topic is Nernst-Einstein relation. The Einstein relation D is equal to U absolute into KT is used to connect the transport process of diffusion and conduction. The starting point is the basic equation relating the equivalent conductivity of A Z ratio Z valent electrolyte to the conventional mobility of the ions, that is to the drift velocities under a potential gradient of 1 volt centimeter inverse. Molar conductivity is equal to F into U conventional plus U conventional minus equation number 1, using U conventional is equals to U absolute into Z I E naught, equation 2. Therefore, we can say that equivalent conductivity is equals to Z I E naught into F bracket U absolute plus U absolute negative, which is equation number 3. Using Einstein relation, U absolute plus is equals to d plus by kt, and U absolute minus is equals to d by kt, equation number 4. Equivalent conductivity is equals to Z E naught into F by kt bracket d plus d negative, one form of Nernst-Einstein equations. We know Na into E naught is equals to F and Na into K is equals to R. So equivalent conductivity is equals to Ze square by RT bracket D positive plus D negative. Next topic is limitation of Nernst-Einstein relation. This relation is not valid where ion pair formation is possible, because in such cases the mobility calculated from the diffusion coefficient U absolute d by kt is not equal to the mobility calculated from the equivalent conductivity, which is U absolute is equals to U by U conventional into Z I E naught. U absolute is equals to d by kt, which is not equal to U absolute, which is equals to U conventional by Z I E naught, which is equals to equivalent conductivity into E by Z I E naught, equation 7. Because on an pair as a whole is electrically neutral and does not feel the electric field, thus ion pairs are not participants in the conduction process. Secondly, the diffusion coefficient is not a constant in general expression derived for diffusion coefficient. D is equals to BRT into 1 plus d ln f by d ln c, which is equation 8. BRT is the value of the diffusion coefficient when the solution behaves ideally, that is f is equals to 1. F is equals to activity coefficients. This ideal value of diffusion coefficient is called capital D naught. Hence, capital D is equals to D naught into 1 plus d ln f by d ln c, which is equation 9. D is equals to D naught into 1 plus D log F by DC, equation 10. Using Debye-Huckel limiting law for the activity coefficient, log F is equals to minus A into C to the power 1 by 2. We have D is equals to D naught into 1 minus 1 by Z into A into C to the power 1 by 2, equation 11. This shows how diffusion coefficient varies with concentration. According to Kohlrausch's law, equivalent conductivity is equals to equivalent conductivity at infinite dilution minus A into C to the power 1 by 2, equation 12. From equation 11 and 12, we can say that the diffusion coefficient capital D and equivalent conductivity have different dependencies on concentration. First is Nernst-Einstein equation. It is valid for dilute solutions only. Next, we have Walden's rule, approximate relation between equivalent conductivity and viscosity. The Stokes-Einstein equation connects diffusion coefficient and the viscosity of the medium, and the Nernst-Einstein equation relates the diffusion coefficient to the conductivity. By eliminating diffusion coefficient in these two equations, we get a relation between equivalent conductivity and viscosity of electrolyte. From Stokes-Einstein relation equation, capital D is equals to Kt by 6 pi nr, equation 1. From Nernst-Einstein equation, capital D is equals to Rt by Zf square into pi, Rt into pi by Zf square, equation number 2. Therefore, D is equals to Kt by 6 pi nr, which is equals to Rt into pi by Zf square. Thus, sorry, it's not pi, it's equivalent conductivity. Thus, from here, equivalent conductivity is equals to Z into F square into K by 6 pi r into 1 by nr, which is equation number 3. But F is equals to Avogadro number into epsilon naught E naught, and K by R is equals to 1 by Avogadro number. We get equivalent conductivity is equals to Z into E naught into F by 6 pi into 1 by nr. Equivalent conductivity into N is equals to constant by R, which is equation number 4. If the radius of the solvated ion is considered to be constant, then equivalent conductivity into N is equals to constant, which is equals to Z into E naught into F by 6 pi r, which is equation number 5. This is empirical Walden's rule. The product of the equivalent conductivity and the viscosity of the solvent for a particular electrolyte at a given temperature should be constant. Walden's rule has some rough applicability in the organic solvents. The product pi into n is different for a particular solvated ion in water and organic solvents and result in the differences in the radii of moving ion.